Okay, let's get started. Good afternoon, everyone. Just a minute. Yeah. So my name is Shiva Poornan. I am a PhD student at the Civil Engineering Department of IIT Madras, and here we are meeting for an live interactive session on the NPTEL course of Matrix Methods of Structure Analysis, and this is the second week that we are meeting. And we are going through the basics of structure analysis and after covering the basics, we'll get started with the matrix methods. So I hope that you remember what we had discussed last week. We were discussing on the basics of structure analysis. So what is static determinacy and kinematic determinacy and stability, and yeah, these were the major concepts that we were discussing. We will continue from there and get into the other concepts that were not covered last time. So before we proceed, I would like to ask if you have any questions so that we can discuss that first.
Yeah, one question that you had left last week
Yes, yes.
that I
So
want
we
to know.
okay. You have any comment on that?
No, actually, I was sick last week, so last week
Okay,
was a bit.
okay, that's fine. Yeah. So any other questions which we did not cover or from what we had discussed, and you wanted to ask any questions on that?
Last week's question only.
Yeah, we'll get started with that. But just before that, I wanted to know if anything else is left out or any is it confusing or something like that. No questions? Okay, then so can someone remind where we had stopped last week? So what was the question that we had discussed? We were discussing. So I hope my screen is visible, right?
Yes, yes.
Yeah. Okay. So what was the
There
question?
was a beam, and both the angles were known.
Okay. So let's say we
And
have a
asked,
beam.
yeah,
Yeah. So simply supported beam maybe.
yes,
Okay. So both the angles at the ends are known. So let's say
yeah.
theta 1 and theta 2 are both are known to us. So
Yes. So, is it enough to ascertain the complete profile or the elastic
yes.
curve of the beam?
Yes, so the question is with these known quantities, can we find out the complete profile of the beam? And what do you think the answer is? Anyone? So basically, if you remember the concepts where we find out the deflection or rotations in a beam, right? So what are the concepts that we use in finding out the displacements in a beam? So we have double integration method, we have moment area method,
Um,
conjugate beam. Yes,
conjugate
yes.
beam.
Right. So if you remember the basic double integration method, then what do we have? Let's say when we are applying moments only at the ends, then how is the moment profile going to vary across the length of the beam? So let's say these two are the moments. Can someone predict what is the bending moment shape? Right. So what is the bending moment shape across the length of the beam? It will be linear, right? Because I know the moment at one end, I also know the moment at the other end.
Yes. That's been,
So those two moments I know and I expect them to vary linearly, right? So if
mhm.
moment is varying linearly, then curvature is also varying linearly, right? If curvature is varying linearly, then what will be the order of the deflection? So this you should be knowing, right? So curvature is equal to m by ei, and we say that this is a linear function of x, right? So let's say first order function of x, ax plus b, right? And we say that the double integration of curvature is going to give us deflection, right?
Yes.
So then what will be the order of deflection? Y is of will be of what order? Cubic. Am I
Cubic.
right?
Cubic.
So what is the general cubic function that I can have? I can have ax cube plus bx
Cubic
square
plus B
plus
square plus
cx
CX plus D.
plus d, right? So there are four unknowns that we don't know in a general deflection profile of a beam.
Yes.
right? So there are only four unknowns that have to be found out in to find out the entire profile of the beam, right? So so that is in a general beam. If we have a beam that is not supported, then to find out its profile after deflection, I should know four things. That's what this equation is saying to me, right? And so the two of the conditions that I already have is that the deflection at this point is zero, or at least I know what is the the movement of this point, right? And I also know the displacement of this point, right? Those two conditions are known, and we assume that there are no axial deformations in this beam, right? So it is just enough to know the rotations at the 2 points to completely find the deflection profile of this entire beam. Is that convincing? So the explanation that we are giving here is that the deflection profile of any beam is just going to be uh, a cubic order. That means that we have only four variables that are to be found out. If you remember what in the last class, what is the degree of freedom that we found out for the beam? We were discussing about kinematic indeterminacy, right? So what is the kinematic indeterminacy of a beam, simply supported beam? Or even without simply supported, what did we find the kinematic indeterminacy of a beam? We said that we need to know
Two
that is,
angles are there.
what is it?
Two rotations at the ends.
Yes,
Two.
two rotations at the end. That is for a simply supported beam. Yes. So if it is not simply supported, if it is free, then what is the degree of freedom that we found out?
4, neglecting the axial deformation.
Yes, so neglecting axial deformation 4, that's the same 4 that we are finding out here through the equations of from our knowledge of Euler-Bernoulli beam theory. We know that the moment diagram is going to vary linearly, and from that we know what is the deflection profile. So since the deflection profile is going to be of the cubic order, we have only 4 terms that have to be found out, A, B, C, D. So if these 4 are known, then it is sufficient to describe the whole thing. Now that means that apart from the boundary conditions of arresting the displacements, we are needing to know only the rotations of the ends. That is sufficient to predict the entire profile. This is true just because we assume that the loads are being applied at the ends only. So when we said that the moment diagram is going to vary linearly, we inherently assume that the moments are going to be applied only at the ends, right? We are not considering any intermediate loads. If the intermediate loads are there, then moments will not be linear. Moment can have a complex variation, right? In that case, this whatever argument that we are talking is not valid, right? So the question of whether the end rotations are sufficient to predict the complete profile of the beam is true only when the loads are applied only to the ends. You have moments or forces only being applied to the ends of a beam, then yes, we can predict the complete profile just using the nodal rotations. If not, then we cannot. So in the stiffness method, we will actually see that what should we do when we have an intermediate load. We'll convert it into an end load. If you remember, even in your basic analysis, you would find out something called fixed end moment and then convert it into moments and then do the analysis. Okay. So I hope this would have given a better perspective of why we are using only rotations. That is true only because we have nodal moments or nodal loads, not intermediate loads. Okay.
Understood.
Yeah. Okay. So this is what we were discussing last time, and then we can proceed on to that and see kinematic indeterminacy, right? So can we find out kinematic indeterminacy of a complex frame system and try to find out and see what it is? So let's say we have a portal frame. So can someone say what is the kinematic indeterminacy of this frame, ignoring axial deformations? It should be easy. So yeah, what is it?
24.
So basically, you need to count the number of nodes that are there, and each node can actually only rotate. They cannot displace because of this configuration. Because take a node, and then if it has to displace anyway, then it has to produce an axial deformation in any of the members. So displacement is completely prohibited. Only possibility is a rotation for each of the nodes, right? So you just need to find out how many nodes are there and multiply by
Well,
1. That's it. So total number of nodes is what is the total kinematic indeterminacy, right? I mean, yes, kinematic indeterminacy, the degrees of freedom of the system. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so 12 is the kinematic indeterminacy of this frame structure, right? Okay. So I hope this gives a perspective of what kinematic indeterminacy and static indeterminacy is. By the way, what is a kinematic determinate structure? We have seen different examples of static determinate structures, right? So cantilever, someone said a simply supported beam. So can someone give an example of a kinematic determinate beam? What is a kinematic determinate beam?
fixed beam.
Yes, fixed beam. So you have basically, what is the understanding of a kinematic determinate beam? Basically, there should be no kinematic indeterminacy. The total degrees of freedom after arresting the boundary condition should be 0, which should happen only when you arrest both the ends, right? So what this means, kinematic determinate beam means what? What is the physical meaning of it?
All degree of freedom are arrested or known.
Yeah, arrested or known. Yes. So we directly know what are the degrees of freedom of this system. We know that the degrees of freedom inherently without solving anything, right? So that's what it means. Okay, but for statics, we again don't know. Just like how in a statically determinate beam, we don't know the kinematics without using other equations, right? Similarly, in kinematic determinate beam, we don't know its statics without using equilibrium conditions and so on, right? Okay, good. So, why do we have these concepts of static determinacy and kinematic determinacy? It is helpful in solving problems of. Sorry for that. So, okay, maybe we'll move on to the next topic and then discuss these concepts. So, what I'm trying to, before I get into what I was saying, we'll discuss how do we find out deflections in a beam. These things I hope you know, just to, for the sake of completion, I'll just write it down here. Deflections in a beam, how do we find out? There are different methods as we said earlier.
From the bending equation calculated, sir.
Yes. So, we have different methods like double integration and we have,
Movement area.
yeah, conjugate beam method. This is one of my favorite, conjugate. And you have moment area method, and you can also have other methods. These are the popular ones, right? Okay, now
Yes.
after this, so what did we study in the previous course? We had seen, okay, this is all about statically determinate beams. Statically determinate beams, we can find out the internal forces from equilibrium. We can find out its deflection from these methods. Okay, I'm not going into the details of this method, I hope you know it, so I'll skip it here. And after knowing the deflections, now we know everything. Basically, from deflections and internal forces, we can find out stresses and strains. Okay, that's what we are at last interested in. We want to know whether the stresses are within the permissible level. So that is what is analysis, right? We are checking its stresses and strains. So we can do that. Coming to statically indeterminate beams, that's what is slightly bit complicated when we see for the first time, right? It's more scarier than statically determinate beams. So statically indeterminate beams, how do we solve them? Indeterminate structures, right? So how do we solve them? There are two major classification of methods that we would have seen last course. Does someone remember that? Statically indeterminate structures, how do we
Energy
solve?
methods.
Yeah, energy methods we can use. Yes, but Energy
So
methods themselves fall
deflection,
into a even bigger class of category. What is that category?
Force method and displacement method.
Yes, very good. So that's what we are getting into in this course. So one is called as force method and another is called as displacement method. So what is the major difference between these two methods? Major way of solving. So let's first give a brief overview of what force method is, which is very easy to understand at the beginning. So can someone give an example of a force method? What is a force method? As the name suggests, basically what we do here is that in a statically indeterminate structure, we know that there are more support reactions or unknown forces that are to be found out in addition to the number of equilibrium equations, right? So those extra forces we treat as redundant forces. Let me give an example before we see this. So one of the example is that you can have a propped cantilever. So in a propped cantilever, let's say this is a roller, okay? So in a propped cantilever,
consistent deformation.
yes, method of consistent deformation is what we immediately think when we see of a prop cantilever. That's how we have been trained. Yes, right. So, how do we solve this problem? I want to know what is the support reaction at, let's say this is A and let's say this is B. I want to know what's the support reaction at A and B. How do I do that? If it
We
were a
use the complete
cantilever, I can do it. Cantilever, I am well
superposition.
versed. Yes.
We use superposition.
Yes, method of superposition we use, right? So how do we do it? What's a way? Can you lead me through
We
the
use the
process?
complete compatibility condition that the
Yes.
joint rotation at deflection at B is 0.
Yes. So yes, exactly. That's a procedure. So what we do is that we find out what is that we split it into two beams, right? Not yeah, you can say two beams, two statically determinate beams. This is first
Yes.
structure, and second structure is the same boundary condition, which is also a statically determinate structure, but we treat the support reaction as if it's a load.
Mm.
Okay, and then we say that okay, there should be a deflection due to the first load, and there should be a deflection due to the second load, right? And we say that the total deflection at this point due to these two loads should be zero because addition of these two things is nothing but this.
Yes.
So the support reaction should be in such a way. This is a redundant force x. We need to find out x. Should be in such a way that the deflection caused by it should exactly negate the deflection that is caused due to the load, and therefore in the total beam the deflection would be zero.
Yes.
Hey, this is a concept. So basically, what we do is that we split it into statically determinate beams. We solve for deflections. Then we use compatibility because we are saying that the addition of deflection should be zero, right? That's what we call as a compatibility equation. So we use compatibility to solve the final statically indeterminate structure, right? So we find out first the redundant forces. We first find out the redundant forces, and then we find out the deflections, and then we use compatibility to solve for the redundant forces. This is one of the methods where this is one of the methods of force methods. So this is called as a method of consistent deformation, as someone said. So why it falls into the class of force method is that because we first treat the unknowns as redundant forces. The redundant forces are the unknown forces. Therefore, it's a force method. Okay. Although this method is very easy to understand, there is a major problem with this method. Can someone point it out? Not a problem as such, it's a minor detail, I would say. What is that which is not very rigorous in this method? The thing is that we had assumed that it's a cantilever with an redundant force, right? But I could have as well imagined the same structure as a simply supported beam. Right, instead of imagining it as a cantilever, I could imagine it as a simply supported beam with this fixed moment being the redundant moment, right? So I could say that it is subjected to a redundant moment here. This is the x that I have to find out, and same load is being applied here, right? So in one case there will be a moment, which is the second case actually, and the first case will be I have just a simply supported beam with the load being applied. and I say that the rotation that is caused due to the load at this point, A point, should be same as the negative of the rotation that is caused due to the redundant moment, and both should cancel each other to make it 0 here. Can I do this way? Yeah, so
Since its system is not stable, even if you want,
The system is stable because if there
which
is
system is not
was
stable? The
it is simply
the
stable.
yeah, this is a simply supported beam, right? It's a stable
yes, it's
system.
stable system.
Yeah, so only thing is that by removing one of the redundants, we would not make it unstable, because if you find out the static indeterminacy, it's of order 1. So basically what it means is that there is an extra support reaction, one extra support reaction in addition to what we actually need from equilibrium. Okay, so removing one of the support forces, okay, here we are removing moment, here we are removing the propped support reaction, right? That will not make it unstable. If we remove two, then it will become unstable. Okay, so this is still a stable system, therefore we can treat this also as a simply supported, and then we can solve this, or we can do it as a cantilever also. So you can do it anyway. There are other ways also of solving it also. Another way is we can remove the reaction at this point and make it a guided roller. Okay, those things are a bit complicated, but it's still possible. So uh, the point that I would like to bring here is that it's not an unique way of solving. So even though it is right and it intuitively makes sense, there can be many different possibilities of solving the same problem. There is no systematic way of doing it. Okay, why this point is very important is because later on we will point this out and say that why kinematic other methods, displacement methods are better. Okay, especially when using computer to solve it, because computer does not want choices. It does not know which to take it as redundant. It gets confusing. Therefore, when we use a computer or a systematic way of solving it, we should not have choices. We should have a very rigorous and unique way of solving it. Okay, so this is one simple example of method of consistent deformation. So in force methods, first well-known method is method of consistent deformation. Any other method in force methods?
Three moment equation.
Yes, three moment equation. So three moment equation is, yeah. So I hope you have gone through the lecture. So I will not go into the detail. I'll just briefly summarize it. So there again the concept is same. You take unknown redundants as the extra forces as the redundants, unknown forces. So for example, if you have a continuous beam, okay. If you have a continuous beam, then what is the static indeterminacy of the structure?
So three.
3 or 2?
No, two.
2. It's just you need to remember that if it was a simply supported, these two things together is a statically determinate. So two extra rollers, so 2, that's it. Okay, just 2 reactions extra. So there are two things, right? So these two things I can just consider out to be the bending moments at these points. Since it's a continuous point, there will be a bending moment, right? What it means is that if I cut it, then it'll have the same slope and it will have a bending moment at that point, right? It does not have an internal hinge. So those 2 points I can take it as a those two bending moments I can take it as a redundant forces x1 and x2. And what will be the corresponding primary structure or the structure which is statically determinate? It will be just a point with an internal hinge, right? So basically we have taken this as a redundant, so without that it will look like a simply supported beam. And the reflection will be something like this. Okay, we can solve this system for these two conditions. One is the applied loads. This method is same as what we had discussed earlier. Okay, so you don't need to get confused here. It's just that whatever we are removing as redundant, then we have to, here since we are removing the bending moment as a redundant, without the bending moment it will look like a simply supported. There is no continuity. Okay, so that's what it is. You can solve that system for both the redundant force as well as the applied force, and you can say that for compatibility, for the slopes to be same. Now it's not same, but to make it same, what should be what the redundant should be. If you solve that condition, you will get an equation. That's what we call as a three moment equation. Okay, so the concept is similar to method of consistent deformation. Okay, so any other methods? These two are the most popular methods. One other method that is very favorite to me is the conjugate beam method. So I'm saying it here, and it's a very easy method to solve problems. Okay, I'll just illustrate it with an example. Let's say that you have a fixed beam and you want to know this is a statically indeterminate beam of order of, what is its order of indeterminacy?
3.
3 if you consider axial
Yeah,
deformations,
2.
but yeah, if you don't consider axial deformation, it's 2, right? Okay, so now what are the unknowns? The fixed moments at the both the ends. So let's say that there is a load that is placed at the center. Okay, so can someone help me find out the fixed moments? So basically solve the system. How do I find the unknowns in the system? Previous methods, we can use the previous methods to solve it, or
Like inverse superposition.
yeah, so
You
principle
can
of
use
superposition, which
principle.
means, yes, what does it mean actually?
Two
So you
moments
can
of
consider it's a equivalent simply supported beam and assume that support moment MB and MP
Are the redundants, and we can solve using the previous two methods that we have discussed.
area moment theorem or
Yeah, so we can just whatever we had discussed, that's what we will do to solve it. But there is a very very convenient and elegant way of solving this problem. We'll see how. Okay, so let me say that the redundants are the fixed moments. Okay, so let me treat this as a, I'll treat this as a conjugate, as a simply supported beam. Okay, with the redundant. So there are two cases here. One is that there is a load being applied, which is the same load that we are applying here, and the second case is that we have the fixed moments that are there.
support moment.
Yeah, so the support moments, let's say x and x equal because it's a symmetric loading case. Okay, so for these two cases, what are the bending moment profiles that will be there in the structure?
First one will be triangular.
One is a triangular.
Yes, so the first one we know it's going to be triangular, so I'll just draw it here itself. Okay, and what is it
It's a
for the second
rectangle.
case?
It's a rectangle. Linear
It's a, yes,
rectangle.
rectangle, perfect rectangle, and then I'm putting it down just for space convenience. Okay, or if it's confusing, what I'll do is I'll do this as positive, so top, this is bottom. Okay, one is negative, one is positive. As you can see, one will sag and one will hog. Okay, so this is the bending moment variation, right? Now if I consider the conjugate beam for this conjugate beam for this beam, what will be the boundary conditions? You remember conjugate beam method? If I have to find out the yeah, if I have to find out the conjugate beam for a particular given beam, what will happen to a fixed support?
Free.
Free, right? So this will become free. The other end also will become free. So this is a
Unstable.
yes, it's a free beam. It's unstable, right, in the sense, but we don't worry too much on it because it's just a conjugate or an imaginary beam. Okay, so in reality we are not going to build it, so we should not worry too much on the instability. But what is important is the conjugate beam should be in equilibrium. Equilibrium is different from stability. I think you should be aware of it, but let me give an example of it so that it becomes clear what I'm talking. Let's say you have ground like this and the ball is just on the top of a mountain. Okay, is this ball stable or unstable?
It is just stable.
There is nothing. I am not understanding what do we mean by just stable.
I mean, slight disturbance will cause instability in the system.
Then it's the term that you're using is equilibrium, so it's not stability. So what we mean by equilibrium is that at
This
this
is
point
unstable.
it's unstable. Okay, So basically, I'll just define what stability and equilibrium is so that we don't get confused after this. Okay, equilibrium means that at this point it's not accelerating. Okay, for the given forces and loads and everything, for the given external forces, it's not going to accelerate. So this ball is not accelerating at this moment, so it is in equilibrium. Okay, equilibrium. It's But then what is the definition of stability? Stability itself means that at a given equilibrium point, okay, we can talk of stability only when it is in equilibrium. If it is not in equilibrium, then of course it's accelerating already, then we don't even talk about stability. Okay, now given that it is in equilibrium, we will say if we disturb it, whether it is going to remain in equilibrium or not. Okay, so that's the definition of stability. So we should not say that after disturbance it will lose its stability. No, now itself, if we disturb it, it will lose its equilibrium, so it is already unstable.
Okay.
Is it clear? So this is an unstable position. Given a small perturbation, it will lose its equilibrium. Therefore, it is unstable. Is that clear?
Yes.
So now we are saying that this beam should be in equilibrium, even though it can be unstable. Okay, we are not worried about its stability because it's not the loads are not going to change because it's a conjugate beam, which it's an imaginary beam. Okay, so this beam, whatever beam that we are talking about, should be in equilibrium. If it is stable or unstable, it's not of much worry because it's not a real beam. Okay, fine. So what are the loads that are coming here? What is the load on a conjugate beam? M by EI diagram, right? So since EI is constant, I'll just draw the M diagram. So due to the load, it will be triangular by EA. Okay, this is factored by 1 by EA, and then this is the loads that are coming, right? So this will be one I'm putting downward, another I'm putting upward. Okay, right? These are the loads that are coming onto this conjugate beam. Now, if this conjugate beam has to be in equilibrium, then it has to satisfy total forces should be equal and opposite, right? So
Yes.
just find this area. What is the area of this thing? If this is P, then this length is going to be PL by 4, right? PL by 4 PL by 4. And what will be this? If this moment is going to be X, this also is going to be X,
Yes.
right? So here it will be PL by 4 EI because I have to do M by EI diagram. So PL by 4 EI and this is M X by EI. So can someone equate these two areas and say what is the X? It's easy to find out X, right? So what is the area of this triangle?
Half into
half
B and
into
touch
half into L into PL by,
EL by
I think
4.
I left a 4 here. Okay, I'm sorry. PL by 4 EI should be equal to
X by
X by EI into L, right?
X by
So what is X?
PL by 8.
EA gets cancelled,
This
LL
is
gets
equivalent to
cancelled.
PL by 8.
Yes, that is all. So basically we have found out the fixed end moment just by using conjugate beam method. Equilibrium of conjugate beam method gives the redundant force. Is this simple compared to other methods that we have discussed till now? It's
Yes, sir.
just one calculation that we did. Only once we had to use a calculation, right? So this I
Yes.
personally find it very easy to solve. So one more example, if you want to see, you can even consider an UDL. Okay, if you consider an UDL, instead of triangular shape, you will have a parabolic shape. So for the parabola, you should find out the area. That's a total downward force that's going to come here. This will remain the same. This will be X by EA into L. Okay, so I can find out what X is again. So that's going to be the same. So I'll skip that sum. What if we have an unsymmetric load? Okay, we were able to solve it because these x and this x are the same, which is true only because it's a symmetric position, right? So what if we had an asymmetric position? Let's say we have the same fixed beam, but the load is asymmetrically positioned. So in this case, can someone help me in solving this problem using the conjugate beam method?
So considered as a equivalent what is it? So, cantilever
Simply
beam.
cantilever is, I don't know, I feel personally easy to consider it as a simply supported beam itself.
Yes, sir.
Okay, Let's take simply supported beam itself. Maybe it is okay to consider as a cantilever. You can try it at home and then say next session whether it was easy or not. Okay, so in this simply supported, what do we have? One case is that we have the same load. Other case is that we have fixed end moments, but the fixed end moments will be different here. It will be x1 and x2. That's the only difference that's going to be there. Now again, if I draw the bending moment variation, it's going to be triangular, but an asymmetrically positioned triangle. And here it will be
Trapezium.
trapezium, yes. So it is going to be higher at which end?
This and x2.
X2, really? Yes, because
Load
that's
is
where
near it.
the load is going to be there. So I'll draw it that way. Okay, so this is what is a bending moment. So now if I consider the conjugate beam, what happens? Again, I have these loads coming in by EI diagram. Okay, we can find out what is the moment here, right? It's known to as P.
PAB, PAB by L.
Yes, yeah, there is something, right? AB by L or something. So then we can do divide by EI, we'll get the total loads that is coming here. And then we can find out what is this variation as well, because how do you find this out? Because this is x1 x2 by EI and that is x1 by EI, that's all. Right, now how do we solve this? There are two unknowns, so can someone help me to solve it? What are the two equations that we need to have so that we can solve for these unknowns x1 and x2?
Reflection is equivalent to 0 and slope also equivalent to 0.
Here we don't talk of deflection in the conjugate
Oh, sir,
beam.
sir.
In the conjugate beam, we are only interested in knowing first it should be in equilibrium.
Yes, sir.
Okay, before we proceed on to anything else. So, how do we, the earlier thing we saw only one equilibrium equation. Usually there are two equilibrium equations, right? One is force equilibrium, another is moment equilibrium.
Moment equal.
Yeah, so here we talked only about force equilibrium. Why didn't we talk about moment equilibrium? Because it will be automatically satisfied because the total forces here will be at the center, right? Because of symmetry, it will be at the center only.
Yes.
Okay, so here also it will be at the center
Center.
only. Okay, therefore if you take the moment about these two forces, it will be any point you take, it will
Same.
definitely be zero. Okay, so it is inherently being satisfied, that's why we didn't take. Here we have to explicitly satisfy, that's the only difference. Okay, so here this total force may be somewhere here, and here also it should be same point. Then only we will know that it will be in equilibrium, right? So we have to explicitly make it happen. So that condition is what will give us x1 and x2. So one equation is that find out this total force. Okay, that will be in terms of P and A and B. Okay, it depends on where the location is. It will be a function of PAB. Now find out the total force that is coming due to this. That will be a function of x1 and x2. Right? Equate them, that will give one condition. The second condition is that find out the center of this load, which we can find out from centroid of a triangle, right? That will be also a function of PAB. Find out the centroid distance from here, that will be also a function of x1 x2. That should also be equal. Otherwise, if they are at two different points, this is a free beam, therefore it will definitely have a couple and it will rotate. Therefore it should not happen. Therefore the centroids should be equal. That condition will give a second equation. Both these equations, when we solve together, we will get x1 and x2. Is that fine?
Yes, sir.
Okay. And we can, it's not that we can solve only fixed beam problems using conjugate beam method. We can even have a propped cantilever, any other type. Okay, let's say we have a propped cantilever. We'll finish this method with the sum. Let's say we have a propped cantilever, and again let's say we have some loading here. So what should we do? Again we should consider it as an simply supported beam. What are the loadings? The loading due to the actual given load is this, and due to the fixed end moment it's just at one end, right? So this is a fixed end moment x. There's only one unknown here. It propped cantilever, there's static indeterminacy of degree 1. So what will be the bending moment variation? Here it will be same triangular, and at the other point it will be right? This is the variation of moment. So again, now when we consider conjugate beam,
Moment diagrams.
yes, moment M
It's
by
not.
EI diagram we can do.
Sir,
Yes, moment by EI diagram we do.
it's uniform, sir. Moment applied support moment at.
Yeah, there is only one fixed end moment,
Oh,
right? So due to the fixed end moment, we'll have a triangular variation, right?
yes.
At the propped cantilever, the moment should be zero. Okay, bending moment should be zero. So this is moment due to the applied load, and moment due to the fixed end will be something like this. So do you think that both the centroids will be at the same position here? No, because the centroid of this thing will be slightly away from the center, right? It will be because the load is more towards this. And for this, it will be slightly to the left of the center, right? Total centroid. I'm talking about the total
Yes.
force that is coming.
Yes. Yes.
But then we should also be careful in doing the boundary condition. At this, for this problem, what should be the conjugate beam boundary condition? There should be a roller here. Okay. Therefore, the centroids need not be at the same point. Okay. So the total load for this part can be something like this, and for this part it can be something like this. Now the unknowns is that what is unknown? The only unknown is x. How do we find out x? There is one other unknown that will come here. When we solve this problem, this will depend only on PAB. This will depend on x, right? But there is also an unknown here. Okay, if we don't want to calculate this unknown, then we have to take moment of these two forces about this point. We should use only moment equilibrium. If you use force equilibrium, then we don't know this force. Okay, so it's better not to use force equilibrium. Directly, if you use moment equilibrium, then we can solve for the unknown x that is here. Is that fine?
Yes.
After finding out x, then if you are interested in finding out this unknown support reaction for the conjugate beam, you can find it out. But that will not help us solve this x. Okay. Fine. I hope this is clear. Any questions at this point in this method? Okay. Then we'll move on to other methods. So we were discussing on the broad classifications of solving statically indeterminate structures. We had discussed on force methods. Now we'll get on to displacement methods. So as I had mentioned out previously also, there are some inherent, even the force methods are intuitively easier to understand at the beginning, but still it is not very the problem with that is that there are different options available to us. It's not an unique or systematic way of solving a problem, and especially while coding it into a computer algorithm. Therefore we want to have a unique or systematic way of doing. That's why we move on to displacement methods. So we'll see what are displacement methods. Okay, so but it is important to notice that displacement methods, to solve it, we should know actually force methods. Okay, without force methods, we cannot use displacement methods to solve it. Why I am saying this is, what did we say as the kinematic determinate beam? Kinematic determinate beam itself is a fixed beam, right? If you remember, I think we had drawn it somewhere. Okay, so a fixed beam is what is considered to be a known thing when we use displacement methods. Okay, that means that we should know everything about a fixed beam. That means what, for a given load at any point in a fixed beam, we should be able to find out its support reactions, its fixed end moments, and so on. To solve that, how do we know that? We would be able to do that only using force methods. Okay, so only when we know everything about a fixed beam, then we can use that information to solve the rest of the problem. Okay, so a kinematically determinate beam is a fixed beam, and that should be known to us. And how do we know that? We know that only from force methods. Okay, so we cannot directly, that's why it is always force methods are first taught, then displacement methods are taught. It's not possible to teach displacement methods directly. I hope that's clear. We'll see an example to understand more. First, before going to displacement methods, let's just talk about some of the prerequisites. Okay, so let's say we have a beam which is supported, which is a simply supported beam. Okay, let's say I give a moment at the end. Okay, so I just noticed that we have 15 more minutes left in this session. I also thought we can cover the assignment problems week 1 and week 2 of previous year. Okay, so do you suggest that we will continue with this topic conceptual discussion, or should we go to assignment problems and then discuss that? Or can we discuss both of them?
Conceptual
Conceptual.
part.
Okay, then okay, anyone else suggesting that we will finish assignments also, because maybe we can cover both of them. We'll quickly finish this and also try to finish that. Is it okay if I extend it by 10-15 more minutes?
Yeah, it is.
Yeah,
For me,
then that's
it's
fine.
okay.
Yes, yes, yes.
Yeah, that's good then. Then we'll see the conceptual things and then we will cover on to assignment problems. Okay, so let's say we have a simply supported beam subjected to n moment m. So can someone say what is the angle of rotation at this point? What will be the angle of rotation at this point? This you can use any of the previous methods that you know, right? So how do we solve it? It's statically determinate beam. It should not be a problem for us. So we can use double integration method. We can use conjugate beam method. We can use moment area method to solve for deflections and rotations, right? And after finding that out, you will notice that theta should be equal to, anyone know by heart this?
3A by L.
PA by L, there is no P, no? Maybe I heard it wrong. What is it? It should be a function of
M by A.
ML by 3EI.
3.
Okay. This is something that you have to start remembering from now on. Okay. So I'm skipping the steps. You can do the steps at your home. So it's very easy. What you have to do is that you can probably use conjugate beam method. For a simply supported beam, it remains a simply supported beam. Then draw the bending moment diagram. So it will be something like this. And load this bending moment diagram and find out its shear force would give you the rotation, and bending moment would give you the deflections, right? So since we are finding out rotations, it's just enough to find out the shear force at this point. Okay, so basically you need to find out the support reaction due to this M by EA, this variation of forces. That's what you have to find out. Let's say there is a force applied onto a beam. What will be the support reaction here? That is what will be ML by 3A. Okay, you can do this at home. It's not very difficult. Okay, so this is something that we would see, right? So what this means is that for any moment, the rotation at a point will be ml by 3a. Does it make sense? Should L be at the numerator or denominator? L being at the numerator suggests that if I increase length, theta will also increase, right? Why? Because when length increases, it will become more flexible, right? So I can rotate it easily. For a given moment, theta will increase more. So it makes sense, okay. And then EI we have. EI is a measure of rigidity, right? So E and I, if it increases, it becomes tougher to rotate. So if E and I increases, theta should reduce. So that also makes sense. So this thing totally makes sense to us. Okay. But so this is a sort of a stiffness to the system. Do you agree? So what I mean by that is, if I write m equal to 3, I am just rearranging this equation, okay? M equal to 3a by L into theta, right? So this is called the stiffness to the system, stiffness of the system.
Yes.
Why? Because this is very similar to a spring equation that I would have studied. Let's say I have a spring and then it is subjected to a force. Then whatever deflection happens, what do I do? If force is sometimes deflection, then that sometimes is what I call as the stiffness of the system. The more the value it is, more difficult to deform it, right? For a given force, deflection will be less, or for a given deflection, force will be more if stiffness is more. So similar understanding I have here, that for a given moment, theta at some point, they are related by some constant, and this constant depends upon the geometric and material property of the system. Why geometric? Because L and I are geometric properties. They depend upon how I design the system. and E depends upon the material
Material.
property, what I use, steel or concrete or any wood, anything. So right, so this is a function of both material and geometric property. M is a function of theta, so this I call as the stiffness of the system. But here you have to remember that we define where theta should be. I could have defined theta to be here, right? If I could have defined theta to be here, then in fact that also we can do. Let's say this is theta dash. Okay, what will be theta dash? Can someone say?
So minus
Minus?
m by
No, I'm just asking the magnitude, right? So yeah, so basically this theta will be just half of this
half
theta.
this. Yes.
Interestingly, it happens to be like that. Okay,
That is.
so if I give a moment to a simply supported beam, try to remember this. Even though I don't prefer to remember things, but later on we will use it so frequently that it is useful to remember. Okay, fine. So if I give a moment, the rotation at this point is ml by 3a, and the rotation at the other end is going to be half of it, which means that it's going to be ml by 6a. Okay. Now if I rearrange this thing, I will get m is equal to 6a by l into theta dash. So this is also stiffness to the system, but it's depending upon what is k theta dash. Okay. So we need to define where the rotation is, where the moment is, and so on. So for a given moment and given location of moment and given location of rotation, we can find out a relation between them using the force methods that we have already studied for any system. Now we have seen determinate system. For indeterminate system as well, we can do that, right? So by that thing, we can actually find out what is its stiffness. Why is it so useful? We'll see later. Okay, in subsequently now. So this is how we find out, right? So what if we change the boundary condition? Does boundary condition have an effect of on this number that we saw? We saw that it will have an effect of the material and geometry will have an effect. But does boundary condition also have an effect on this? What do you assume? What do you think? Guess. Hmm? Let's say that I have a propped cantilever and I give the same momentum. I want to find out same rotation here. How will the displacement rotation diagram use something like this, right? So let's say this is theta. So the relation between m and theta, how do I find out? M is going to be something of theta. So what is that something going to be? We can find out, right? We know statically indeterminate beam, yes, but then we know how to solve it using the force methods that we have already seen. One of the recent methods that we saw was conjugate beam method to solve these problems, right? So we can use conjugate beam method to find out the fixed end moment. After we know fixed end moment, everything is known. After we know the free body of the structure, we can find out anything, right? After we know the free body of the structure, we can find out the internal shear forces and bending moments, and once they are known, double integration, we find out the deflections. That's it. Rotations. Whatever we want, we can find out. So that's why we stopped at the point of just finding the fixed end moments. After that, we didn't discuss because once fixed end moments are known, all the free body is known. Once the free body is known, everything is known. Okay, so that's why I didn't discuss further on that. So using that method also we can solve this problem. Okay, so maybe you can try it at home to convince yourself, but the number that would come up here is that it will be 4 by L. Okay, so instead of 3 by L that we saw earlier, M is equal to 3 by L into theta, it comes out to be 4 by L. Should it be 4 or should it be 2? How do we know? Let's say we are confused and we don't know. We know that it is going to be 3 by L for a simply supported case. So should it be higher than that or should it be lower than that? Let's say that we didn't know. Hmm? The stiffness, will it be higher than 3 by L or will it be lower than 3 by L?
Lower than 3.
Higher than 3 by L, because when we fix it on the rear end and on the other end, it will become more stiffer, right? It becomes more difficult to deform. That means that the stiffness value will increase, and that says why it has become 4 by L. Okay, exactly why for that we have to calculate, but at least we know that it will increase from 3. Okay, So this comes out to be 4 EIBL. And here you would have known that the fixed moment is just half of the moment that you give. Yeah, okay, that's fine. That's of not very much important to us right now. What we note here is that the boundary condition also has an impact on the stiffness. So it's the three things that we had seen: boundary condition, material property, as well as geometric property, the length and the dimensions of the beam itself. Okay, so one more boundary condition we will see probably. Let's say we have a guided roller.
So what actually guided roller, sir? But you please,
What actually it means in practical condition, how is it built, you're asking, or what it actually means theoretically, you're asking?
uh, we know the roller, but guided roller means
Okay,
how do
guided
you?
roller basically means that it will maintain the so it is like a fixed cantilever itself. Okay, so it's
Yes,
like a fixed cantilever, but the support whichever is being fixed to it, right? Let's say a plate or something is being fixed to the beam, right?
yes,
That plate is made to slide along a wall. Okay, so what will happen if this thing is made to slide? Then it can freely come down. This whole total thing can come down here, right? The plate.
yes,
If the total plate comes here, then the rotation would something like it will be this beam will be always perpendicular to this thing because it's fixed to it. So the rotation will be something like this. Okay,
yes.
for a given load, depends on the load. I'm talking about a case where the load is something like moment is like this, then it will just deflect here. Okay, I'm sorry, this need not meet at that point. My intention is that it will just deflect up. It depends on the position.
Yes, sir.
Only guided roller we cannot have. It's a unstable system, right? Because a cantilever itself is a determinate beam. So once we remove one of the support reactions, what are we removing? We are removing the shear force at this point. Once we remove the shear force, it becomes unstable. So we need to have one more support here to make it
So
stable.
drawer would be a guided roller system.
What is it?
Drawer.
Yeah, a drawer is an example of a roller, I would say, right? Because you're not having any in drawer, you are having only rigid body displacements, right? We are not having a deformation in the system itself, right? When you draw something, when you have a drawer, it is a rigid body. Totally, I think that it's just a roller thing. You have a drawer on it, so it just comes off.
Yeah.
It's just a mechanism. There are no stresses and strains being produced on it if you don't have friction or any other thing coming into the picture. So it just moves very freely. Okay, so
Is
that's
this like
how.
something sliding in a slot? The other
Yes,
end.
yes. This path you're saying, right? Yeah,
Yes, yes.
it can have a slot. Yes, it can have a slot. Only thing is that
Windows.
it's rigidly fixed for rotation. Rotation alone is not allowed. But
You
the
told that
total,
it is.
yes. What is it?
No, no, please continue.
Yeah, so the plate that is attached to the beam only will slide, but the plate will not rotate or something like that. The plate will still remain vertical.
Okay, okay, understood, understood.
Okay, if it is allowed to rotate, then this total beam also rotates. So basically, this beam will always remain horizontal at the starting point.
Only shear force is eliminated, but
Yes, exactly, exactly.
understood.
So we are eliminating only shear force here, and a fixed moment will be still there.
Okay, okay.
Okay, so this deflection shape will be something like this at the point. Okay, so if you have a guided roller, okay, it can be hinged or whatever we give, and let's say that we have a moment. So can you? I have already drawn the deflected shape, but can you guess, will it move upward or downward for the given loading condition that I have drawn here?
Upward.
Why upward? By the way, cantilever, what will happen? Let's say I have a cantilever and then I give the same load here. Okay, loadings are same. Only thing is that instead of this prop, I'm having a cantilever, changing the boundary condition. What do you think will be the?
It will be
Uh,
hogging.
it will be hogging. Yes. So this deflection point will go downward or upward. This point
That should go
Downward.
downward.
downward. Yes. So here, what will happen?
This should, no, this will remain, yes.
Hmm?
Yeah, so same in the other beam above. If we just translate that diagram on the lower right, lower left corner, then uh, it should go up.
Up.
That point,
Yes.
the point is fixed, so the
Yes.
other point will move up.
Yes, exactly. So basically, as he rightly pointed out, this beam. So here I want to. Okay, after finishing this, maybe we can discuss it. So the thing is that it is very identical to a cantilever in terms of deformation. What we mean by deformation? Deformation is just the internal strains that are happening within a structure. Okay, displacements are different. Displacements are also includes a total rigid body displacement. Okay, but deformations are internal. Okay, so basically the deformation for this and this will be identical. Only difference will come in displacements. Okay, so I'll make it more clear when we discuss on the concept of free body and other things right after this. So the answer to this is that we cannot have a deflection at this point, but if you see the bending moment will be same for these two. Okay, so what will happen is that it will deflect like this. It should also hog because the bending moment will also be same. You can try to find it out because it's a determinate beam. Okay, you can try to find it out. You will see that it is also hogging. The only way it can hog is that if this point moves up, because this point cannot move. So that's a answer. Okay, so here I want to point out that if you draw the free body for this structure and this structure, both will look similar, and it will also be similar to a half of a simply supported beam. So we have a simply supported beam with, let's say, n moment applied. Okay, then half of it, if you see, that is what is actually a very good example of a guided roller, right? Why? Because the shear force is zero here, and it will allow it to move freely along this line, right? And if you even see the free body diagram of it, it will be same as this. So it will deflect similar to this. That's it. Is that clear? Maybe in the next class or sometime we can discuss in detail on what is the effect of boundary condition, where all you can have free bodies to be the same, and so on. Okay, those concepts you will get in detail as you solve many problems and try to see many book questions and solve it. Okay, this detailed understanding is not needed right now. Now what we are discussing here is that for this boundary condition, for a given moment, what will be the rotation here? Okay, so can someone say what is the rotation here? This question is same as asking for a given moment what is the rotation in a cantilever. Okay, so does someone know that theta for a given m? It will be ml by e. So at least to say should it be lesser than simply supported and so on? Yeah, from this analogy you should be able to answer it. Anyway, I'll give you the answer here. You can think about it later in your free time. You will find that it will be equal to m is equal to ei by l times theta. Okay, so it will be very flexible. So that's what is the stiffness to the system. Why I am saying all this is, let's say we have a problem. Okay, so before we go to the problem, I'll summarize what we have discussed. We discussed that in a simply supported beam, the moment and the rotation at the same point are related by 3 ei by l. Okay, the stiffness to this system is 3 ei by l. And if we change the boundary condition from simply supported to a propped cantilever, then for the same moment, everything else remaining same, only the far end being fixed, then the stiffness increases from 3 a by l to 4 a by l. Okay, if we have, instead of the fixed end, if we have a guided support, then we have a ei by l stiffness to the system. Okay, this is what we had discussed till now. Now we'll use this information in solving a problem using displacement methods. Okay, let's say we have a system like this. Maybe I can start with an easy example. Is this a statically indeterminate problem? Yes, to the order of 1, right? Now let's say that I'm giving a moment here at the center. Can someone say what will be the what is the kinematic indeterminacy of this problem?
Two.
2. The rotation at this point and the rotation at this point is unknown. Everything else is known. Now, can you find out what is the rotation at this point? Using the information that we had discussed now, let's say this is L and so on. Other things you can assume, okay, this is L, this is L, total Young's modulus is E, okay. Now, can someone relate M and theta that will happen at the same point?
4A by L theta.
That is true when we have only the cantilever, right? We also have something else coming to the right, right? So what you can do is that we know that this total moment can be split into two things. A part of this moment will go on to deflecting this part, and a part of this moment will go on to deflecting the other part, right? And so how much we know that the rotations are going to be same in both the cases, right? So is this system in being in parallel or series? Deflection is same, but loads are getting distributed. What is that system? An analogous system could be this. You have force 1 and two springs K1 and K2, okay, and you have a block, and if you put a force here, what will happen to that force?
Distributed to
Yes, distributed to both of them. A part of this force will go to this, a part of this force will go to the second spring, but both will have same deformation, right? Same thing is happening here. The rotations are being same here, but the part of this moment and deforming both of the things is getting distributed, right? So the system is in parallel. So we can say that the effective stiffness of these two systems is going to be. So how do you find out the effective stiffness of these two systems? If they are in
K1
parallel,
K2 by
what
K1 plus
condition do you?
K2.
What is it?
K1 K2 by K1 plus K2.
We need to think on that. Let me ask you a question. Okay, when we get confused with whether it is 1 by k is equal to 1 by k1 plus 1 by k2 and k equal to k1 plus k2, how do we find out which is the right answer? Let's say we are sitting in an exam and this confusion comes up. Right now it has come to me, that's why I'm asking. So
By
how do we
equating
remember it?
deflection for the case of parallel.
Yeah, but an easy way that I think is, anyone have
Are
an
you
easy way
asking
of
for how to derive it?
how to
If
derive
like,
is the second level. So we don't have time to derive it. I just want to know which one is right. I know any one should be right? If I
yes,
don't
yes,
know
yes.
anything, if I'm completely blank, I have to derive. But if I know one of these two things is right, I can at least reject one of them, right? So how do I reject? So do we think that the stiffness of the total system should be more than the stiffnesses of individual system, or should it be less than that?
More than that.
More than.
Exactly, because we are just giving more and more support. It's like a structure. We are building a structure. We are supporting more and more at the bottom. It is to help the system. The deflections will reduce, right?
Yes.
But if you have a series system, what will happen is that the deflection here happening, what is happening here, plus the deflection that is happening here. So the total deflection will increase, which means that the stiffness is lower, getting lesser and lesser here in the system. If we are adding more and more supports here, then it means that we are making the system more and more flexible or lesser and lesser stiffer, right? Here
Yes.
in this case, we are adding stiffness. That means that K should be K1 plus K2, right?
Yes.
The other way, if you do, you'll find out that we are actually reducing the stiffness. Okay. So we use the same formula. So what is K here? K in this thing, I know that for the first thing, moment to theta relation is what is K, right? So I know K is equal to 4E by L. K1. What is K2? You're understanding what I'm saying? This is K1. So if you have the stiffness offered by this beam is going to be 4E by L because the far end is fixed. I know what it is. It's a propped cantilever, right? Propped cantilever subjected to M1. M1 is a part of M, right? So that will have the stiffness associated with that is 4E by L, right? And what will be K2? K2 from the
Three.
second spring?
3A.
3A by L. So the total stiffness is going to be 7A by L,
3A.
right? So what will be the total rotation? Just m by theta, right? So I mean m by k, right? So m is equal to k theta. Total m is equal to total k into
Stiffness.
total theta. Theta 1 and theta 2 are same as theta, and that is equal to theta. So we know that m is equal to k is going to be 7a by L times theta. So theta is equal to ml by 7a. That's it. Solved.
Yes. Yes.
So for any given moment, we can find out what is the rotation that's happening at this point. Is it not very simple to solve this?
Yes.
Yes, yes, yes.
So that is why displacement, and this is the only way we can, not only way, there are different methods, but at least the kinematic variables are only one if you are interested only about this point. Okay, it is converted to a single kinematic variable problem because we know the behavior of a simply supported beam. This is also a variable, I agree, but later on we will see how to use it as a two kinematic variable problem. Right now we have converted into a single kinematic variable problem because we are not actually finding out what is this theta. Okay, and we know that information that the stiffness offered by this is going to be 3a by L. So with that we are able to convert it into a single kinematic variable problem, and then we are able to just solve it using the conditions of equilibrium, right? So just like how in first method we used compatibility to solve, ultimately here the last step would be to use equilibrium and then solve the problem, right? So you can solve the same problem if the support conditions were different. So I'll stop with one complex problem, not complex, it's a little bit complicated than what we saw now. Okay, so let's say we have a frame structure, something like this. Okay, let's say we have a roller here too, a fixed support here, and a hinge support here. Okay, now let's say there is a moment that is coming on here, m, and same moment is being applied here. Can we find out the rotations at these points? So the length level, you can take it anything that you want. Okay, it's just an example problem, so I'm not too much concerned on the values. It's 2L. So how do we solve this problem using the concept that we right now saw? What is the first step? What we can take advantage here? We can take advantage of symmetry, right? It's a symmetric structure, so we can say that the center, about the center, we can cut it and say that we'll analyze only one half of it. Right, it's making use of symmetry. We know that this point cannot move horizontally, because if it has to move horizontally, which way should it move, left or right? We cannot be biased towards any one thing because it's symmetric. Therefore the only way it can move is vertically, right? And also it cannot rotate. That means that the total beam cannot have a rotation, because if it is clockwise or anti-clockwise, why clockwise or anti-clockwise, both the sides it's looking the same, right? So the only way it can move is it should have a zero slope at this point. Okay, so it should move here and it should have a zero slope, so the beam should look something like this after deflection, I'm saying. Okay, I'm not worried here what is happening, I'm just saying at this point the rotation is zero, and at this point only vertical displacement can happen. That's the point that I'm trying to show here. And that means that what is the effective boundary condition at this point? Can someone say? We had right now discussed what this thing should be taken as. It's a guided roller, right?
Shear
We can,
force is 0.
yeah, shear force is zero, bending moment only can be there. Therefore it's equivalent to considering it as a boundary guided roller. Okay, so this equivalent problem I can write it as the same problem here: hinged, a roller, a fixed, and a guided roller. Now this problem, can we do we know to solve it? Yes, we know to solve it, right? This is again a springs in parallel or series?
Parallel.
Parallel, because the rotation is going to be, deflection is going to be same, the forces is going to get distributed, right? So this k1, this k2, k3, k4 we have to find out. Do we know k1, k2, k3, k4? What is k1? K1 is going to be 4a by L.
4A by L.
Yes. And what is K2? K2 is
CA.
slightly bit complicated. Let's see who says it. Look at the boundary condition here. What have we given here? It's a roller, right? Think about how will we, so when we find out K1, how did we do it? We just split it into one cantilever and then we say that it's a pin joint here, and that pin joint and prop cantilever, what is the stiffness, right? Same thing if we try to do here, what will we observe? Let's say we are having the structure, it's a roller and there's a pin joint, right? And if I rotate, if I give a moment, what will happen to this point? Is my screen visible or should I draw bigger?
I don't know.
Okay, so basically let's say we have a pin here. Why am I drawing a pin here? Because I know that point cannot move. Okay, that's why I'm able to consider it as a pin, and then we say that it's a prop cantilever and so on. Okay, that's an inherent assumption that we are taking here. Why this point cannot move? Because they are all actually rigid. Okay, fine. So what will be the stiffness to the system? Since it's a roller, it just move, right? This is possible only because it's perpendicular. Let's say you have a roller and you have a perpendicular member like this, then it doesn't resist this motion, right? That's the whole reason. Okay, so if it would have been inclined, if I would have drawn a roller here, then it's also 3A by L, like a pin, simply supported beam. But the roller is not there, the roller is here. Okay,
Zero?
yes, K2 is 0. There's no stiffness associated with it. The deflection shape, if you see, it will be like this. Ultimately, at last, it will just give away. Okay, fine. Okay, so 0. What is K3? EI by L, right? We saw for guided roller, what is the stiffness? EI by L. Okay, make it a habit to remember these things. Also check it once. I'm not sure whether it should be 2 EA by L or EA by L. I think it's EA by L only. Anyway, check it once with the standard books. K4 is, what is K4? 3A by L, yes. So that is all. So total stiffness is going to be an addition of this. 4 plus 3 plus 1 is 8. 8 EA by L. So I know moment is equal to 8 EA by L times theta. So theta I can find it from inverting it. ML by 8A. That's all the answers. So it looked like a complex problem, but we have solved it within like 3-4 steps. Right? So that's how powerful displacement methods are. Okay. Hope this would have given a flavor of why we need to study displacement methods.
Yes, yes.
Okay. So I think we have ran out of time. So probably we can discuss the previous year assignments if you are really interested in it. Okay, because what I observed was that the questions are all simple. So I think that it will be getting very boring if I start to discuss them. Let me know if you are stuck with the problem, and then we can discuss on that problem only. Okay, or if you have time in the next class, probably we can discuss all 1 to 3 week 1 to 3 problems in the next session. Okay, any other questions, or shall we stop the session here? Okay, if there are no questions, then probably we can stop the session here. Thank you for attending.
Thank you, sir.
Thank you.
Wait, now?